Hello all, welcome to my YouTube channel. So this is episode number 13 and we are continuing with the deep learning with Pytorch series. So while building a neural network, we generally need to make a lot of choices, right? So some of the choices are like you need to choose the correct activation functions. You need to choose the correct loss functions when designing a neural network, right? So the two choices which we will see today is like the choices of activation function and also the choices of loss function. So the idea is to give you an heads up and an idea like how you can choose the activation function, and it is kind of a layer wise, right? In hidden layer and the output layer, what are the type of activation function you should use, and depending on the problem like either regression or classification, which can be a binary classification or a multi-class classification, what are the type of loss function you should use, right? So let's get started. So we will start with choices of activation function, right? So sigmoid activation function is a very basic one which we also talked in detail when we were going through the logistic regression. Here like the activation output is like 1 divided by 1 plus e to the power minus z, right? And if you just, so I am also showing you the derivatives of my activation functions here. So if you see for higher values of z, right? So if I just take a highlighter here. So if you see for the higher values of z, so z is in the x-axis, and the output of my activation function is in the y-axis, right? For higher values of z, if you just look at the derivative here, the derivatives are uh, close to zero, right? So higher values of z, and also for higher negative values of z, also your derivative tends to close to be zero, right? So we know from our previous experiences or from previous sessions that weight updates happen with this equation. Your W equals to your previous W multiplied by learning rate times DW, right? So here we see the DW are very close to zero, right? So this operation, this multiplication of learning rate with a value which is close to zero, that will give you a very small value, right? So the weight updates will not be happening properly, or the weight updates will be in a very small magnitude. So the weight updates will not be proper in the sense using when you are using sigmoid activation function, right? And it can also slow down the gradient descent convergence process because we are taking small steps where the derivatives are very close to zero. Okay, now next moving into the next activation function, which is TanH activation function. So generally this TanH activation function works better than your sigmoid activation function. So TanH, the formula of TanH is e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. So this is the formula which I was talking about, right? So generally we use TanH in the hidden layers of my neural network, and sigmoid activation function, which I already talked about, that we generally use at the output layer when we are doing with the binary classification, right? So if I now look at the derivatives of my TanH, right? So here also you will see your derivatives are very close to zero for higher values of Z, which is like a positive Z value, and also derivatives are very close to negative values of large negative values of Z. So here also it comes with a slower convergence, but it has certain advantages. So here the values are scaled between -1 to +1, which you can see here, and here it's kind of has an effect of centering the data where the mean is close to zero rather than zero point 0.5, which happens in case of sigmoid activation function. So as the data is kind of centered to mean, so the later layers which are after this hidden layer with a TanH activation function, there the learning would be much more easier, right? Because the data is kind of centered to zero. Now the downside of this activation function is again, which I talked about, for the higher values of Z, your derivatives are very close to zero. So the learning would be again slow down if you use this activation function. Now there is another kind of activation function which we call as Relu. So in Relu, which is kind of the most used activation function, and in the hidden layer, by its nature, we generally use Relu as an activation function in all the hidden layers. And the formula of Relu is when the value of z is greater than 0, then the output of this activation function would be equals to z. And when the value is less than 0 or equals to 0, then your activation function output value would be 0. Right. And if you just look at the derivative of this z, so when the values are less than 0, then the derivative is 0, right? So this is where your derivative is 0. And when my z value is greater than 0, then my derivative of my Relu activation function is equals to 1. So for when the derivatives, when the z value is negative, then your derivative is 0, right? So if I go back to the equation of w equals to w minus learning rate times dw, so this dw will become 0 when my z is less than 0, right? So here the learning will not happen, and your learning would be much slower, right? So this has the problem which comes with Relu. So to tackle that, we use a different variation of this activation function, which is, sorry, which is leaky Relu. So for the values of z, when the z is negative, we multiply the z with an with a hyperparameter which we call as a, and that we generally multiply with the z value, and it gives a small slope here which will cause your derivatives to not become 0 when the z is less than 0, right? So that's the thing which we use also in nowadays, like leaky Relu you can straight away use in the activation, in the hidden layer activation functions, and that will give better results while comparing with the TanH or Sigmoid activation function. Okay, now moving on, there is a special case of activation function, what we call as Softmax activation function. So you need to remember, we use Softmax activation function when we are doing multi-class classification, and we only use this at the output layer, right? So previously, the things which I talked about, like Sigmoid, we generally use in case of output layer. So just writing it down for you. This is we do it in case of binary classification, right? Then we talked about TanH and Relu and leaky Relu. So that we generally use at the hidden layers. And this softmax we use generally in case of when we are doing a multi-class classification. That is when we are doing a multi-class classification, multi-class, yeah, classification. Okay, now what this softmax activation function helps us to do, right? So before going to the output layer, we in the output layer, in the end, we need the probabilities, right? And probability has to be in the range of 0 to 1. But before going to the output layer, your logits, so generally we call those as logits. So if I just visualize with this example, and just let me erase these things. So if I take this example, like I have my input, which is X, then it passes through a linear layer, which does the W transpose X plus B. Then we get the logits, right? And this logits can be of any range, right? But in the output layer, we need the value which needs the sum of those values needs to be a 1, right? Because we are aiming for the output values, the probability values, which should be the sum of those probability values should be 1. Here you can see 0 0.7, 0 0.2, and 0 0.1, right? So we can choose based on this. This is the distribution is, if you sum the distribution of this will be equals to 1, right? And we can select the probability or the class with the highest probability value. Here we can select 0 0.7, which has the highest probability value, and we can give that as an output to my neural network, right? Now, how we do it, right? So we have 2, we have 1, and we have 0.1. Now, the calculation for 7 will happen in this way. So what we will do is we will do e to the power 2.0, and we will normalize this value with this e to the power 2, then e to the power 1, and e to the power 0.1, right? So this is the denominator which we need to have to normalize this value. So that's what also I have mentioned here. So this is kind of summing. After taking the exponential value, we are summing and normalizing the value of each of these probability values. Similarly, for this value will be e to the power 0.2, right? And similarly for this one, which is 0.1, it will be to the power 0.1. And each of these cases, we are dividing the value by the sum of the exponential terms, and we are just normalizing the value so that the output distribution sum is equals to 1, right? And so as I mentioned, this softmax activation function we generally use when we are doing a multi-class classification, right? Okay, and in Pytorch with this method, you can access the softmax. So generally, like in Pytorch, it is a log softmax instead of a plain softmax. So why it's taking a log? It's just to give a more numerical stability to the neural network optimization process. Okay, now let's go to the choices of my loss function and how we can which loss function to choose based on your a type of problem that we are working on. Now, loss is nothing but the inconsistency between your predicted value, which is y hat, and the actual label, right, which is y, right? So that is the difference we try to measure, and based on that, we try to understand how well the model is performing based on the loss function output, right? So in case of mean squared error is kind of a default choice, which we generally use in case of regression problems. Here we just square the values of my y hat and y, and then take the average of this. So if I just write it down, it's like y hat minus y whole square divided by the total number of examples, right? So that we generally use in case of mean squared error. Then we also have negative log likelihood loss. This generally we use in case of multi-class classification or binary classification, right? So here, the thing you need to keep in mind, uh, here we generally use this negative log likelihood loss when we use a softmax in the neural network itself, right? So the model has to have softmax at the last output layer. So then only we will use this negative log likelihood loss, right? So this we generally use for classification task like multi-class classification problem. And as I mentioned, this is a very important point, which is like use only on models with the softmax function as an output activation layer, right? Uh, then we have another function which we call as cross entropy loss. So in the cross entropy loss, this we also use in case of multi-class classification, and in case of binary classification we use this BCE loss, which is binary cross entropy loss. So these are the PyTorch notations which you need to keep in mind. This is for multi-class classification, and in case of binary classification we use BCE loss. But the mathematical operations which you do in case of cross entropy loss and negative log likelihood loss is absolutely same, just that in PyTorch it is the operations are different. So in case of PyTorch, if you use this cross entropy loss that is coming from torch.nn, your softmax is already incorporated in this function. So your cross entropy loss is kind of a combination of your negative log likelihood loss and log softmax, right? So it is like softmax plus your negative log likelihood loss will give you this cross entropy loss, right? Cross entropy loss in PyTorch is a combination of softmax and negative log likelihood. So whenever you are using loss function, which is cross entropy loss, you should not use softmax at the output layer, because it will do the operation of softmax twice. So your output will not be proper, right? So this you need to be very mindful of when you are working with PyTorch, when to use cross entropy loss and when to use the negative log likelihood loss, right? So in case of this example, which I am showing here, let's try to understand how the negative log likelihood works. So here we have certain inputs which are like images of cat, horse, and dog. Then we get based on the input values, we get the logits, which are like for every class we have logits, which are like 5, 4, and 2 for cat, and 4, 2, 8, and 4, 4, 1 for the other two examples. Then we take a softmax out of it. So the softmax will kind of make the distribution sum equals to 1. So if you just sum across all these values, that will be equals to 1. Similarly for this, right? And we select the value with the maximum probability score, right? For this, the values which are with underscore or underlined, that is the correct class, right? So here the value is 0.71. So if you take the negative log likelihood value, then your loss would be like 0.34, which is kind of lower in value. But it should have predicted with a higher confidence, right? So if you look into this example where for the correct class, the probability value is 0.98, which is very close to 1. There you will see the negative log likelihood value is very small because it's kind of it's giving an incentive to the model for predicting the correct probabilities for the correct class. But when it is kind of giving you a lower probability for the correct class, it's kind of still penalizing you, right? And similarly for here, you will see it is confused with these two classes. So here, the loss is the negative log likelihood loss is the highest value among these three, right? So with this, you can understand like what the negative log likelihood or the cross entropy loss works. But just you need to keep in mind in case of PyTorch, when to use cross entropy loss and when to use the NLL loss, right? So yeah, so that's all I had for this video. So in the next video, we will try to do neural network implementation with all the concepts we have learned so far till this video. So if you like this video, please share with your friends, subscribe the channel, and also like this video. Thank you all. Thanks for your time.